So the next application I want to talk about, and I'm using the word application kind of loosely here, is this thing called the mean value theorem. The mean value theorem it's a very useful tool, don't get me wrong, but it's not the kind of thing I can really ask a lot of questions about. I mean, I could, but they're going to be mechanical rather than application oriented. The mean value theorem is one of those things that's useful more for other things that it lets us prove. For example, in the next lecture, we're going to talk about how to tell when a function is increasing versus decreasing. And the mean value theorem is going to be fundamental to proving the rule that we're going to use. So I'm going to talk about it on the next slide, tell you what it is. And at that point, you're welcome to bow out. And go on to the next lecture, and you can read about listen to my discussion of increasing and decreasing functions, and you'll be just fine. Okay, so here's what it says. It says if we have a function, and this is you're going to hear these requirements over and over again throughout the rest of the class here. It's continuous on a closed interval, differentiable on an open interval. We're willing to cut a little slack on differentiability on the endpoints, and it still works. Then there is at least one point in C. There's at least one point C in that interval where this is true. Now that may look a little bit of a mess, but let's think about this for a minute. This right-hand side is just the derivative, right? And I want you to think of these in terms of slopes, right? This is the slope of the tangent line. And now this left-hand side here, flash back to the very beginning of class, but before I even talked about what the derivative is, right? This f of a minus f of b over a minus b, this is the slope of the secant line through the endpoints of the interval. All right, so let's take a look at this visually, because I think that'll help. Let's say I have my point A here, and I have my function, and I don't want to go that far. I have my function here. Right, so this is A, and this is B. Right, so the left-hand side, that is the slope of the secant line. That's the slope of this line here. And what this mean value theorem is saying is it's saying that there has to be some number between A and B where the slope of the tangent line at that point is equal to the slope of the secant line, or if you want to think about it geometrically, it's parallel to the slope of the secant line. Okay, now like I said, I could give you a function and endpoints and ask you to find the C, and then it's really just a glorified algebra problem. Really, this mean value theorem is more interesting because of other things that it lets us claim. So let's take a look. So like I said, I mean, I could ask you questions. I could give you a function and say, find the value of C where the mean value says has to exist for this interval. But that's not a very interesting question. It really is. You take the derivative and then it turns into an algebra problem. The mean value theorem is much more interesting for the things it lets us show. Right? So here, take a look at this thing. All right, what this is saying is if the derivative of a function is 0 at every x on an interval, right? The derivative is constant, it's 0 everywhere. Then the function is equal to a constant. If you think about this, that maybe looks a little familiar, right? Because when we first started talking about the power rule, one of the first things we showed is that if f of x equals a constant, then f prime of x is 0. Well, what we're showing here is the converse. We're going the other way around. We're saying if the derivative is 0, then the function is constant. All right, so let's see how we can do that. All right. First, pick two numbers between A and B. Because I want to show that for every number on that interval, f of x is a constant. So pick two numbers. Let x1 and x2 be on this open interval. And assume they're different. Right? Let me actually write that in there. And x1 not equal x2. Okay, what does the mean value theorem say? The mean values theorem says there exists a C. You see, we've already used C for the constant up there. But that's okay. There exists, use a lowercase c, there exists little c on the interval such that f of x2 minus f of x1 over x2 minus x1 equals f prime of little c. Okay, but wait, the derivative is 0. Right, that was our assumption, that the derivative is 0 for every number on that interval, including c, which means f of x2 minus f of x1 over x2 minus x1 is 0. All right, let's clear the fraction. All right, let's get rid of x2 minus x1. They cancel on the left side. F of x2 minus f of x1 equals x2 minus x1 times 0, which is 0. All right, but look, move that over. F of x2 equals f of x1. And that's what I needed to show, right? You pick any two numbers on that interval, and they have the same function value. The only way that's going to happen is if the function is equal to a constant. Okay, so that's nice. Right now really what we've shown, if I want to summarize this, we've shown that f of x equals a constant if and only if f prime of x equals 0, right? It goes both ways. All right, so how about this one? This is an interesting question. Suppose we have two functions and their derivatives are equal to each other everywhere. Right? Their derivatives are always the same. The obvious question to ask here is, does that mean the functions are the same as well? Well, it turns out they're not. Right? This is not enough to make the functions equal. And we can see this with a really quick example. Suppose I let f of x equal x squared and g of x equal x squared plus 1. All right, obviously, those functions are not the same. However, their derivatives are both 2x. The derivatives are equal. Okay, so here's what we can say. We can say that if two functions have the same derivative everywhere, their derivatives are equal, then the two functions are equal, give or take a constant. Right? F of x is equal to g of x plus some number. All right, plus a number. All right, so how can I show this? Well, there's a neat little, I always hate to say tricks because there are no tricks in math, right? It can be subtle sometimes, but not tricky. But this is a technique that you should maybe be familiar with. All right, I'm going to define a new function. I'm going to say let h of x equal f of x minus g of x. All right, so then what do I know about this function? I know that h prime of x is equal to f prime of x minus g prime of x, one of our earliest derivative rules. But I know that f of x and g of x are equal. Well, if f of x and g of x, or excuse me, f prime and g prime are equal. Well, if f prime and g prime are equal, then their difference has to be 0. And that means h prime of x equals 0. Okay, but now flash back to that last corollary we talked about. The last corollary said if the derivative of a function is 0, then the function is equal to a constant. Right? So because h prime of x is 0, h of x equals a constant. But look, what was h of x? h of x was f of x minus g of x, so that equals the constant. Move the g of x over. F of x equals g of x plus c, and that's what I wanted to show, right? So if two functions have the same derivative, they're not quite equal to each other. They're equal to each other, give or take a constant added on to one of them. Okay, so those are good things to know, right? You can hopefully see how this mean value theorem is letting us kind of get some additional insight into the properties of the derivative of a function. In the next lecture, we're gonna go back to a more concrete example. We're gonna talk about how we can take this mean value theorem and kind of parlay into a method for determining whether or not a function is increasing or decreasing on an interval.